Okay, now jumping into some resisted motion. Most of our questions from now on will involve particles that have some mass, and to account for this, we're going to use Newton's second law. So we're going to get so sum of forces equals to mass times acceleration. Now, force is a vector, acceleration is a vector, but we can consider them in terms of components. So we consider them in terms of x, y, and z components. So that helps to come up with like a net force expression for each dimension, effectively. So to build a differential equation to solve these motion questions, we need to sum up all the forces involved and then apply Newton's second law. Most forces should be given to you, or at least described in the question, and you may have to draw free body diagrams to resolve forces. That's very important, and it's even something that turns up in the extension 1 syllabus when we were talking about vectors. Drawing free body diagrams, it feels like more of a physics thing, but it's very important to do with mechanics, because mechanics is effectively physics topic, just with calculus in it. I enjoy it. When a particle moves through a medium, it is subjected to resistance. The resistance acts in the opposite direction to the motion. E.g., if the particle falls vertically, the resistance acts upwards. If the particle is projected upwards, the resistance acts downwards. Now, that seems a bit wordy, but effectively what it's saying is if you throw a ball upwards, right, the ball experiences a drag in the opposite direction to motion, so it's pulling it downwards alongside gravity. If you drop a ball, say, from the top of a building, the air resistance acts opposite it, and therefore it acts against gravity. The resistance is pretty much always opposite the velocity. So drag and friction is pretty much opposite motion. Some cases, I think the majority of cases is the same. Resistance forces, acting to oppose the direction of motion. When an object moves horizontally, we can avoid gravity. Instead, we look at resistive forces such as friction, which acts in the opposite directions of velocity. And these are just a couple of integrals which may turn up, which are quite useful, so I just threw them in there. So if a particle of mass m is fired upwards with initial velocity v through a resisting medium under the influence of gravity, g, let y be the height of the particle above the point of projection, and time t, the only forces acting on the particle are the resistive force and the weight, thus the net force is that, and we can come up with an acceleration expression. The sort of very important thing to do with these sort of questions is to define a clear axis system. So or a sign convention. So if we're going to assume positive is upwards, right? Then if we're looking at the forces, we've got gravity downwards, right? So it's going to be minus mg. And we've got air resistance also downwards, minus mkv to the power of n. And usually n is usually 1 or 2, depending on the situation or depending on the particular problem. So the net force is going to be the gravity, which is pulling down, so minus mg, minus mkvn, which is also pulling down, equals to my dot, double dot, sorry, mass times acceleration in the y direction, and you can do a bit of cancellation, and that will give you y dot equals minus g plus kv to the n. Okay. When a particle travels vertically through a medium, only two forces act on the particle, force due to gravity and the resistance motion. Typically, it is found that the resistance is proportional to the power of speed, v, thus the resistance equals minus mkv to the n for some constants. Sometimes it's not mass dependent, so you won't see an m in there, but most resistance, air resistance in particular, is proportional to the square of the velocity, but it's some power of n. Sometimes it's 1, sometimes it's 2 usually. Sometimes 3, very rarely though. But in the question they will definitely specify, so you don't have to sort of come up with it yourself. The only forces acting on the particles are gravity and air resistance. So this is in the case of, again, upwards is positive. This is in the case of, if we take downwards as positive, my mistake. If we take downwards as positive, in this case, and the particle is launched upwards, particle is falling downwards in this case, we get mg acting downwards, but because the particle is falling downwards, air resistance acts in the opposite direction, so we get minus mkv to n. And so the net force is going to be your downwards gravity, which is going to be positive because we assume downwards is positive, minus mkvn, which is upwards. And it's a negative because we assume downwards is negative. And that's going to say mass times acceleration is that. We can divide through by mass, and we end up with that expression here. And this is a differential equation which you've potentially seen some of in extension 1. So yeah, not too hard. Here is a example of particle with resistance. Let me just have a quick look in terms of time. Shouldn't be too bad. We have quite a few examples, but I think this one's definitely worth going through. It's a 4 marker, so it's not something it's going to involve potentially a bit of work, but hopefully not too much. Sometimes 4 markers are nice to you, and there'll be ones where there's just a little trick in there that you have to use in order to get the answer. Sometimes it can be grueling and a lot of work. Sometimes a very small little trick can really simplify the problem. So you get 10, 1 minus kv squared. That's the acceleration. And we're asked to find the velocity of the particle after 5 seconds. So we're looking for a velocity-time relationship. So let's start. Let's start with, again, we're looking for velocity and time. So what version of acceleration should we use? We should use dv dt. So yeah, dv dt equals to 10 times 1 minus kv squared. And if we reciprocate it, we end up with dt dv equals to 1 over 10 times 1 minus k squared v squared. If we expand it. Now, I won't go through the partial fractions in detail, but in order to integrate this function, you're going to have to use partial fractions. And so I'm just going to jump to the partial fractions because I'm sure you would have done at least a few of them in the further integration topic. So I'm just going to jump through that. Now, this isn't in a form that we can easily integrate like that. So we're going to have to use a bit of factorization. And that's one of the reasons that they gave it to us in 1 minus kv. Sorry, that should be outside kv squared like that. The reason they gave it to us is in order for us to identify that it's a squared minus b squared form, so difference of 2 squares. Yeah, and so we get 1 over 1 minus kv, 1 plus kv, and so using partial fractions, that should show us that that's equal to 1 over 10 integral of 1 over 1 minus kv plus 1 over 1 plus kv dv. Okay. From there, we can integrate this. These are just ln functions, so we end up with 1 over 10 times, that should be a half. Now, the partial fractions also ends up with a half, so this should be 1 over 20, that should be 1 over 20. And we can pull out the k when we integrate them, so we get ln 1 minus kv minus, 1 plus kv ln 1 minus kv, just by using integrals, and then we just reshuffled them, so we put the positive at the front, negative at the bottom, negative on the other side. And so from there, we can express that as t equals to 1 on 20k ln 1 plus 2k, 1 plus kv, 1 minus kv, right? And so when and we've got the plus c as well, because it's an indefinite integral. Now, in order to evaluate the plus c, again, we look back at the question, look for initial conditions, and that is that particle starts from rest. So that means that t equals 0, v equals 0. So if that's the case, we get 0 equals to 1 on 20k ln k times 0, so 1 over 1, which is 1, plus c. ln 1 is just 0, so we end up with c equals 0. And therefore our expression becomes t equals to 1 on 20k ln 1 plus kv of 1 minus kv. Right? Now, they've actually given us the value for k, but before we sub it in, we're looking for v in terms of t, right? We could, at this point, try and rearrange for v, but I think it might be actually quicker in order to solve for v after we sub in the numbers. So we have at t equals 5, we end up with, and we can sub in our t as well, we end up with, and we can bring the 20k up, so we get 20k times 5 equals to ln 1 plus kv 1 minus kv. And so we end up with 20 times our k value was 0.01 times 5 equals to ln 1 plus kv over 1 minus kv. And nicely enough, the left-hand side, if you evaluate that in your calculator, turns out to be 1. So we end up with ln 1 plus kv over 1 minus kv equals 1. And so if you exponentiate both sides, we end up with 1 plus kv equals to 1 plus kv over 1 minus kv, is equal to e. And again, if we sub in k equals 0.01, doing a bit of rearranging, I'll skip the rearranging steps, end up with v equals to 100 e minus 1 e plus 1, which is 46.2 meters per second. So yeah, for 4 marks, bit of work, but not terrible. Okay. We will potentially skip the following question. It's an inclined plane question, not terribly difficult, but it is something that actually is required in the Extension 1 syllabus to be able to do. That is to resolve forces on an inclined plane. This one is just with the forces in with a resistance force as well. So you've got the gravity force pulling you down, and you've also got a resistance force. I encourage you to do this one in your own time as well. And part 2 is the slide down as constant speed. Okay, that's just solving for. So we've got the resultant force. We can look for the acceleration and looking for the specific value of v in which the constant speed, which is acceleration, is 0. Yep. Okay. This is an interesting question. This is from the 2020 HSC Extension 2 paper. We do have quite a few practice questions. This one again is resolving forces. So I think what I want to do is quickly run through this one, which is forces on the object, because it's not something that's quite often sort of really emphasized enough, in my opinion. So we've got, when we look at the forces on the system, now the proper way to do this is to look at the forces on each individual mass and try and compare that. Although that's not, that's more of a physics approach. Although I think it's equally valid, and I think that's the better approach. But even NASA has suggested sort of doing the approach in which we use the sort of looking at the forces on the system as an entire system, if that makes sense. So we have the 4 mg, right, pulling it downwards. And let's just say anything that assists the motion downwards is positive, anything that resists the motion is negative. Now that's not the best sign convention to use because sometimes it's hard to tell what's assisting motion, what's resisting motion. But in this case, it's not too complex of the system, so we can do that. So we can say that the net force is equal to 4 mg, right? That's assisting motion. But then we've got resistance on that block. So we can say minus kV. And then we've got a 2 mg. Is that assisting motion or is that opposing motion? Well, if 4 mg is moving downwards, the 2 mg is sort of counterweighting on the other side and it's pulling downwards. And so we get minus 2 mg, right? And then that block also experiences an air resistance, hence the minus kV. And so if we use that and simplify a bit, we get 2 mg minus 2 kV, right? And that's equal to mass times acceleration. The mass here, the net mass is 4m plus 2m, so 6m times A. Again, it's looking at the forces on the entire system rather than individual blocks, but the individual block approach should still work. And so we end up with the acceleration. If we divide through by 6m, is going to be mg minus kV, doing a bit of simplification, over 3m as required, or gm. That's the way they like to write it. Okay. You can choose either one of these. I reckon, looking at the time, we can probably do the second one, I think. But they're quite similar, but the second one's a bit more interesting. So I have particle A of unit mass traveling horizontally through a viscous medium. When t equals 0, the particle is at point O with initial speed u. The resistance on particle A due to the medium is kv squared, where v is the velocity of the particle at time t and k is the positive constant. When t equals 0, a second particle B of equal mass is projected vertically upwards. So we've got a unit mass particle that is initially having speed u, particle A, and it experiences both a gravitational force and a resistance due to the medium. The resistance on particle B is kw squared, where w is the velocity of the particle at time t. The acceleration due to gravity is g. Now show that the velocity v of the particle A is given by 1 over v kt plus 1 over u. Now this is a good question because it combines both horizontal and vertical resisted motion, and so we can sort of get both covered in one shot. So first thing to draw a diagram. So we have particle A that we're interested in first, and that one's traveling horizontally. Right? So that's our velocity. And if we look at the net force, and the sign convention that I'm going to use is to the right is positive. So, and therefore we have the force of resistance acting to the left of kv squared. So if we look at the net force, which equals to mass times acceleration, mx double dot, and I can use x double dot here because we're talking about the horizontal axis, and x-axis is usually our horizontal axis. We get minus kv squared is equal to mass times acceleration. Now the mass here is 1 because it's a unit mass. So we get x double dot is minus kv squared. Okay, and here we have an acceleration and a velocity relationship. So which form of velocity should we use? Well, if we look at what we're trying to prove in the question, if we bring up the slides quickly, but look at what we're trying to prove. We're trying to prove a time expression. So we got 1 on v equals kt plus 1 on u. So if that's the case, then we want a velocity-time relationship, so we're going to use dv dt equals minus kv squared. And so if we reciprocate both sides, we end up with dt on dv equals to minus 1 on kv squared. And so we end up with time as being the integral of minus 1 on kv squared. And that's just going to be minus 1 on k, integral of v to the minus 2 dv. So using power rule, we end up with minus 1 on k times minus 2 v to minus 1 plus c. Oh, sorry, my mistake. Shouldn't be there, that should be v to the minus 1 plus c. And so we end up with t equals to minus 1 on kv plus c. Now, let's go ahead and multiply through by k. And it doesn't really matter what we do with the constant because it's still, again, a constant. So we get kt equals to minus 1 on v plus c. And in order to evaluate what c is, we need some sort of initial condition, right? And that's where the t equals 0, v equals u comes in. So that's our initial velocity. T equals 0, v equals u. So we have 0 equals to minus 1 on u plus c. So that must mean c equals to... Oh, sorry. This negative here cancels. That should be positive, positive. Yep. Positive 1 on u, so c equals to negative 1 on u. And so our expression becomes kt equals 1 on v plus 1 on u. Right? Yeah. Okay. So that's part 1. Part 2, by considering the velocity w of the particle b, show that t equals to 1 on root gk, tan inverse, so and so, so and so. Okay, now this particle b is a case of vertical resisted motion. So if we look at the axis as being, if we take the sign convention as being upwards as being positive, so if we take upwards as positive, and we look at the forces that are acting on the system, we've got minus g, right, gravity pulling it down, minus mg effectively, but remember mass is 1, so it doesn't really matter. Minus mg, and we've got a resistance of kw squared, right, which is also pulling it downwards. Because it's launched upwards, the resistance is also pulling it downwards, minus kw squared. Okay, and so we get acceleration is equal to, well, mass times acceleration, but mass is a unit. So we get minus k omega squared, or w squared minus mg, and so we get acceleration equals to kw squared minus g because the mass is 1. And so our expression becomes dw dt equals to minus kw squared minus g. Right. Now the reason that we use our velocity time relationship, that is our dv dt sort of relation, is because we've got t equals something something in terms of u and w, right? And that means that we have a velocity time relationship. So let's go ahead and integrate this. Let's take the reciprocal. dt on dw equals to minus 1 on g plus kw squared. We can then integrate. Time equals to the integral minus the integral of 1 on g plus kw squared dw. Now this may seem like a tricky integral, but if we write it in this form, if we pull out a factor of 1 on k, maybe it becomes a bit more obvious what this is. It's g on k plus w squared. Well, if we have something plus something squared in the denominator, that usually indicates we've got some sort of trig, right? Trig function, or inverse trig function. In this case, it's tan inverse, and so that the thing inside the brackets for tan inverse must be the square root of g on k. So that implies that we get t equals to minus 1 on k, minus 1 on k times root k on g, because the reciprocal of the inside brackets has to be at the front. Tan inverse W root K over G plus C. Right, and we can put the C outside if we'd like. It doesn't really matter. And so we end up with the expression, if we do a bit of cancellation with this K and the K out inside, we get T equals to minus 1 on root GK, right? Because we've got a half a power on the top, whole power on the bottom, so we can turn that into a half a power on the bottom. Tan inverse W square root K on G plus C. Right. Now to evaluate the constant here, we're going to have to use some initial condition. So looking back at the problem, we're told that at t equals 0, second particle is projected vertically upwards from O with the same initial speed u. So that means at t equals 0, v equals u, or w equals u in this case. So that means that we end up with c equals to 1 on root gk tan inverse u, because we replaced the w with a u, square root k on g plus c. Sorry, the c we moved on the other side. And therefore, our new expression therefore becomes t equals to 1 on root gk. Now this is a longish expression, but you just have to be careful with things. Tan inverse u root k on g minus 1 on root gk tan inverse w on root kg. Okay, and so our t expression, if we pull out a 1 on root gk, now this is pretty much what we're looking for, so I'm just cleaning it up and into the form that they've specifically asked for. Tan inverse of u square root k on g minus tan inverse w square root k on g, and so we're done. Okay, so that was part 2, 3 marks, not too bad. Show that part 3 says show that the velocity of the particle A when particle B is at rest is given by that. Okay, it's an interesting question. So when particle B is at rest, we're asked to find the velocity of particle A, right? So if particle B is at rest, that means that W equals 0, right? So if W equals 0, let's see what that gives us in terms of our time expression. So if W equals 0, our time expression becomes 1 on root gk tan inverse u root kg. That's just a constant, remember, that's all constants, minus tan inverse of 0 times square root k on g. Now tan inverse of 0, that's 0, hence this term cancels out, and so we are left with t equals 1 on root kg, or root gk, tan inverse of u times root k over g, right? And we're asked for the velocity of particle A when particle B is at rest. So we got the when, that is what time that occurs. Now we're looking for what is the velocity of particle A. Well, our velocity of particle A, we came up with an expression for that in part 1, which is 1 on v equals to kt plus 1 on u. And so subbing in the t value that we just got there, you get k times 1 on root gk tan inverse of u times root k over g plus 1 on u, and doing a bit of combining fraction, or this is an expression for it, but yeah, actually that is the expression that we're looking for. So we get 1 on v equals to 1 on u, so if we pull the constant out first, and then we got root k on g, so that means that we've got k over square root of gk, so that means we got root k on g, because we've got a whole power, half power on the bottom, so that means half power on top, tan inverse u root kg. Okay. Finally, part 4. Hence, if v is very large, hence if u is very large, explain why v equals 2 over pi root g on k. Because we have a expression here in terms of u, right? And we're looking at when u is really large. That just means that we're looking for what happens as u approaches infinity. So if u approaches infinity, this term here, 1 on u, becomes really, really small. That becomes negligible and 0. Root k on g, tan inverse of in pretty much a really, really big number times some constant is still going to be a really, really big number. Now, tan inverse of a really, really big number is just going to be pi on 2, right? So we end up with 1 on v equals to square root of k on g times pi on 2. And if you're ever in doubt, have a look at the tan inverse function graph, and you'll see that as x goes to positive or negative infinity, positive infinity approaches pi on 2, negative infinity approaches negative pi on 2. And so taking the reciprocal, so we get v equals to square root g on k times 2 over pi. Or the way that they wanted it was v equals to, now they shouldn't be that concerned about which order you write it, but it's better to just write it in the way that they're looking for. Okay. So moving on. Again, the slides do have a few questions in there for you guys to try on your own. They are pulled from past HSC papers, but definitely recommend giving it a shot yourself before you actually look at the solutions. Okay, so to find terminal velocity, just a little side note before we end up on resisted motion. To find terminal velocity, that's just what happens as a limit as t goes to infinity of v of t. Just like for position, right, we took the limit as t goes to infinity. Similarly, we take a limit as t goes to infinity for velocity to see what the terminal velocity is, or what the limiting velocity is, sometimes it's called. It's pretty much, if you're in perfectly vertical resisted motion, we end up with, so if you have the net forces being mg this way and kv squared that way, or kv this way, dependent on that, we get mg minus kv squared, if we take downwards as positive, equals to mass times acceleration. And if we set acceleration equals 0, that is, when the velocity approaches the terminal velocity, the acceleration becomes slower and slower, right? Because it's approaching that velocity and it's almost hit that maximum velocity. It can't go any faster than that. That means that the acceleration is approaching 0, and so we end up with mg equals kv squared, and so we get v equals to the square root of mg on k, or if it's a unit mass, or if it's not a square expression, we get mg equals to mkv, for example. Then we end up with the m's cancel, so you have v equals g on k, the limiting velocity. And if you were to graph it, you should see something like this. Approaches that value, that's our terminal velocity. Okay, so it looks like about 50 in this case. Just a sec.